Now that we've stated the equivalence principle, let's see how gravity is different from the other forces. To do this, we're going to have to turn the equivalence principle into real mathematics, so that we can do calculations that involve both gravity and relativity. And to do this, we'll introduce the concept of proper acceleration, which is measured by an accelerometer. If you're inside a car and the driver steps down hard on the gas pedal, causing acceleration, you will feel as if you're being pulled towards the back of the car. This feeling of being pulled backwards is your body feeling proper acceleration. So, proper acceleration alpha is the acceleration measured by an observer in their own reference frame relative to an inertial reference frame, and proper acceleration is measured with an accelerometer. An accelerometer is made of a rigid outer box, with an inner ball that is electrically and magnetically neutral. The ball is balanced on springs that are attached to the outer rigid box. The spring compression is what helps us measure alpha. The larger the spring compression, the larger the proper acceleration felt by the accelerometer. In some examples. Let's say that we're in deep space and there is a rope that is attached to an accelerometer. If the rope pulls the accelerometer forward with constant force, then the outer rigid box will get pulled forward, but the inner ball will lag behind, until it is pushed forward by the spring. This results in the spring compressing. Since one of the springs is compressed, the accelerometer measures a non-zero proper acceleration alpha. Because the ball pushes up against the spring, the accelerometer can tell it is now in a non-inertial reference frame, caused by the force of the rope pulling on it. Now, if we have an accelerometer where the outer box is made of iron, it will get pulled toward this magnet. Now remember, the inner ball of an accelerometer is always electrically and magnetically neutral, so it will not feel attracted towards the magnet. Once again, the outer box will get pulled forward, but the inner ball will lag behind, causing spring compression. So once again, non-zero proper acceleration is measured. If the outer box has a rocket attached to it, which applies a force, as the box gets forced forward, the inner ball will again lag behind, causing spring compression, and so we measure a non-zero alpha. Now, what about the case of an accelerometer moving in free fall towards the Earth? Since both the outer box and the inner ball will have the same acceleration relative to the Earth's center, this means that the inner ball will travel with the exact same motion as the outer box, meaning there is no spring compression, and therefore proper acceleration alpha is measured to be 0. We can see here that gravity is different than other forces in nature that we've seen, because gravity acts on both the outer box and the inner ball equally. So when an accelerometer is in free fall, it measures a proper acceleration of 0, just like we'd expect for inertial frames. So we've seen that gravity is not like other forces. When an accelerometer is in free fall due to gravity, it measures 0 proper acceleration, just like we'd expect in the case of an accelerometer in deep space traveling in an inertial frame with no forces acting on it. Because free fall does not result in any proper acceleration, we're going to make an important change to our thinking in physics and say that gravity is not a force at all.